In this probability problem, we're going to consider a machine which has two components, and these two components are going to be in parallel. So let's just quickly draw the system just to illustrate what's going on. So we have two components. Here's component 1, here's component 2. Let's just colour these things in. So let's call this component 1 C1 and component 2 C2. I want to get from A to B. So clearly I can get from A to B provided at least one of the two components functions. Now I will make an assumption, and this assumption is that the components are what we call independent. So this is a very important word. This means that whether component 1 works or does not work has no effect on whether component 2 works or does not work. So independent events, think of it as, let's say you toss a coin. If you get ahead on the first toss, this will have no effect on the outcome you get on any subsequent tosses. Okay, those events are what we call being statistically independent. So let me also assume that the probability that component 1 works, which I'm going to denote by P of C1, let's assume this is 0.7, so component works with probability 70%, and the probability that component 2 works, written like this, I will say is 0.8. So my question that I want to work out is the following. What is the probability that this machine works? And we've already said that this machine will work if either C1 is working, or C2 is working, or both are working. The only way I cannot get from A to B is if both components fail. So using our set theory notation, I can write this as the following. It's the probability of C1 union C2. Because remember, this union notation, this symbol here, in words, what does this whole expression mean? Well, you can read this as C1 and or C2. So it's at least one of these two components. So I can write this in another form. And if you turn to your subject guide, you will see this notation used. The probability of C1 union C2 is the same as the probability of C1 plus the probability of C2 minus what we call the intercept, probability of C1 and C2. So this symbol here, remember, denotes the intersection. So why do we have to do this? Well, just going to an aside, let's consider this very simple Venn diagram. Suppose I had two events, A and B, denoted here. If I wanted A union B, what area is that? Well, that's going to be anything in A or B or both. So that's all of this green shaded area here. Now, if you consider this as the following, so therefore the probability of A union B is going to be the probability of A plus the probability of B minus the probability of the intersect, A intersect B. And why is that the case? Well, think about it. So let's just pick some different colours. So if I want the probability of A union B, the probability of A is everything in A, which is this whole circle here. Okay. Plus the probability of B, let's pick black. Probability of B is going to be everything in the B circle. But the trouble with that is that I've double counted the intersect twice. So the intersect, which is going to be all of this area here, okay, this is being counted twice, so double counted, therefore I have to subtract it once. Okay, so returning back to our component problem, what is the probability of C1? Well, I know that that is 0.7. What is the probability of C2? Well, I know that is 0.8. So what about the probability of C1 intersect C2? Well, to solve for this, I'm going to make use of this independence assumption. Because if two events are independent, then, so for example, if I had the probability of A intersect B, where A and B were independent, then this is just going to be the product of the individual probabilities. So, for example, consider tossing a coin. Let's just go down here a moment. what's the probability of getting a head on the first toss and a tail on the second toss? Well, those events are independent, so it's just going to be the product of the individual probabilities, namely the probability of getting a head on the first toss multiplied by the probability of getting a tail on the second toss. Assuming I have a fair coin, then the probability of a head or a tail is they're both going to be equal to a half, so this is just going to be a half times a half, which is a quarter. So if you see the word independent in your exam question and you're dealing with intersects, then you are going to be multiplying probabilities. So returning up here, this will be minus the probability of C1 intersect C2, so it's going to be the product of probability of C1 times the probability of C2. Plug all this into your calculator, so 0.7 plus 0.8 gives me 1.5, minus 0.7 times 0.8 is will give me 0.56, which gives me a final answer of 0.94. Notice, had you forgotten to subtract the intersect, so let's say you just computed the probability of C1 plus the probability of C2, in this particular question, notice that that answer would have given you 1.5. And remember that a probability is always between 0 and 1. So if you get an answer for a probability which is not between 0 and 1, you should know automatically that you've committed a mistake somewhere. So if you do get either a negative probability or a probability greater than 1, well, that isn't a probability. So retrace your steps, find out where the error has occurred, and correct it. Right, there's also one other way of working out this question. So this is my OR method. The probability of the machine working is going to be 1 minus the probability that the machine fails. Okay, so the probability that the machine works equals 1 minus the probability that the machine fails, because clearly the machine either works or it fails. There are no other possibilities for this machine. Why might I want to work it out this way? Well, we will see in just a moment that I've got fewer events to consider. Because when does this machine fail? This machine fails when both components fail. So there's only one possibility for that. Whereas in the case where I was considering the probability of the machine working, I had to consider 3 cases, as denoted here. Namely that it's either component, well, this here, C1 union C2, one or both components, as given by a probability of C1 plus the probability of C2 minus the probability of the intersect. So over here we had 3 probabilities to consider. If I use this approach, I only need to consider one probability, because this is going to be the following. Let's just be consistent and use our blue. 1 minus, well, what is the probability of the machine failing? Well, I'm going to introduce this notation. It's probability of C1 complement intersect C2 complement, where the complement, which is this little symbol here, if you like, denotes not or the opposite of. So, for example, the probability of complement of C1 equals the probability that C1 fails. Okay, and this is just 1 minus the probability of C1, where C1 denotes the component working. So what is this going to be? It's going to be 1 minus, well, C1 and C2, these components are independent, so whether I'm dealing with an intersection of complements of C1 and C2 or not, these events will still be independent. Whether the component works or fails is independent of the other component. So again, I'm going to multiply these probabilities together. So what is this intersect probability? Well, what is the probability of the complement of C1? Well, we can see from over here that this is just 1 minus the probability of C1. So this will be 1 minus 0.7. If component 1 works with probability 0.7, it fails with probability 0.3. And I multiply this by the probability of component 2 failing, which would just be 1 minus 0.8. Okay, so this will just give me 1 minus 0.7 is 0.3, times 1 minus 0.8 is 0.2, which is 1 minus 0.06, which is equal to 0.94. So notice I've obtained the same solution regardless of my method. I get 0.94 in both cases, and I must do because these are equivalent approaches. This is the same probability that the machine works. So either you could use either approach. It just depends if you're comfortable with working with complements. It might make the computation a bit easier. Okay, so always do a quick feasibility check. Make sure your probability is between 0 and 1, because if it's not, you know it's wrong. But be aware that there can be more than one approach to a particular probability question. So do note whether events are going to be independent. If they are, it should be clear from the question that they are, because that simplifies the work we have to do, and because we are going to use this sort of result, where if you're working out the probabilities of intersects, you just take the product of the individual probabilities. So rerun through this example, make sure you follow through how it's all done.